Okay. Welcome everybody to the senior design oral presentations for the fall semester. We got 4 talks in this session this morning. The first is about a composite surfboard, and so I'll let the teams introduce themselves and go at it. You got about 20 to 22 minutes for the talk, and then there'll be Q&A. So take it away, guys, whenever you're ready.
Well, as he said, welcome. This report, as you screen right now. So first, we'd like to introduce our team. I'm Sydney. I am our team lead. This is Ethan. He is our materials person. This is Fern. He is our manufacturing person. This is Dakota. He is our truss designer, as you'll learn more about that later. And this is Lauren. She is our finite element analysis. So we'd like to mention Greenhouse Surfboards, as they are a custom surfboard shaping and fabrication company here in Milwaukee. Their mission is to create eco-friendly surfboards to show that they can be eco-friendly and eco-beautiful. So our question here really isn't what is Greenhouse Surfboards, it's really who is Greenhouse Surfboards. Greenhouse Surfboards is Dr. Ken Cole, who is here with us today. He is our motivation and inspiration behind this project. He is looking to create a more sustainable and eco-friendly surfboard, which is the mission that he's given us. So you can see pictured here, he is standing with the surfboard that doesn't have anything wrapped around it. That is a truss system from someone else who made it that he's standing with. You'll see more here that were made by other universities or people that he's worked with. But our goal is to create something similar here, than a foam core surfboard. So with the design process, we define the problem to be solved. That's where we got to begin. What are we trying to fix? We're trying to fix the disposal of a foam core surfboard that negatively impacts the environment. We are working with Greenhouse Surfboards, Dr. Ken Cole, to get the knowledge and resources to make better materials that are biodegradable, that have the same or better properties than foam core surfboards. So after we define the problem to be solved, we're going to prescribe objectives and constraints. Now, constraints is what we have to meet. This is our goal that we are going to meet in the end. Objectives are just our wants, where we want to be besides constraints, are above and beyond. So to constrain this surfboard, we would like to use materials that are only jute and epoxy. Those are only materials we are going to be using. The board is going to be able to hold up to a 200-pound person, but we'd like it to hold up to more than that. That was what our factor of safety is going to be. 1 1/3 of a 200-pound person. But we are really shooting for double that weight. The board needs to be ridden 5 times without major failure. The manufacturing process must be able to be replicated. And the board has a truss design, not a foam or solid center. The board is also going to be biodegradable. What we want is for the fin to have, or for the board to have a 1 fin setup. It should be optimized to reduce weight, meet all of our safety factors and standards that we have set, have a standard shape design, minimize production costs, and of course be aesthetically pleasing. So next in our design process, after we have prescribed our objectives and constraints, we are going to investigate background information and state of the art. Throughout this presentation, we will see background sprinkled throughout before we explain each part of what we are doing.
So you see, actually, none of us are actually huge surfers, but here, for those also that are similar to us, we did a bunch of background research. And so here are just kind of some common components or just pieces of the surfboard. So you have on the top the nose and the tail on the bottom. You have the deck, which is the top of the surfboard. You have the bottom of the surfboard. On the sides, you have the rails. And you also have the rocker, which is just how far either the tail or the nose has gone from the lowest point on the board.
So throughout our presentation, we are going to start with the basics, the materials that we are using. Ethan will be talking about this section. Fern will be talking about how we are going to manufacture this board. How are we going to get it done? Dakota is going to be talking about our truss design and shaping decisions and our approach to making a board. And Lauren will be talking about the finite element analysis and how we are simulating and making sure a board's going to work before building it. So in making these design decisions, we're going to narrow it down to optimize solutions using a decision-making matrix, also known as a Q matrix.
So first things first, this is jute. This is the burlap sacks from Collectiva coffee bags. We need to figure out a way to turn this into material that we can use to build a board. And the way that we do that is what's called the composite. There are two main physically distinct components of a composite, and that's the reinforcement and the matrix. Now you see in this picture, these long circular tubes are meant to replicate reinforcement. And what they do is provide most of the strength and the stiffness to the composite. Now wrapped these reinforcements is the matrix, and that kind of provides the shape of the material and a protective coating to the whole thing. And when we started making composites, because not a lot of people know, the material properties that come from jute and epoxy, right? So we have to find our own. And we ran into some issues when we started making composites, and that's these voids or dry spots that happen when you make the composite. And then what it is between these fibers are called interstitial regions, right? And what happens is the matrix does not fill this void. And so we leave little holes, right? And it's not good for geometric properties. So if you go to the next one. So we combat this issue is we try to thicken the epoxy, which was what you can see here. Originally, epoxy is like very clear. And what we've done is we've added polyethylene fibers here that turn it a little bit white, but it also makes it a lot thicker. Increasing the surface tension of the epoxy and the viscosity, making it thicker, helps it bridge the gap between these fibers and fill those voids better. Originally, we had two approaches, which is one to wait out the cure time of the epoxy. So as the epoxy cures, it gets thicker until it becomes a solid, right? But we got too close to the work time of the epoxy, so it would solidify completely and we wouldn't be able to do a layup with the jute fibers. So we opted for the polyethylene approach, and it's been working out. As you can see here, this is a tensile test. This is how we get our properties. What it does is it pulls it this way and measures the exact amount of force and how much this sample stretches along that force. Get to the next one. This is the data that we get from that. Without the epoxy modified, you can see these sharp discontinuous jumps in displacement. That's the matrix of the epoxy breaking. Since it's brittle here, you can see these sharp jumps where it jumps down, and then we end up with ultimate failure, which is where the composite breaks completely, right? After we added these polyethylene fibers, you can see it's really, really smooth, which is nice for data, but it also means that the matrix has become more ductile. This creates an issue if you go to the next one. This ductile situation means that we have local elongation, which is where a section of the fiber pulls apart a little more than the rest of it. And when you calculate Young's modulus of the material properties of it, you use geometric properties like deformation, which is like small changes in length over the full length. So we either need to shrink the full length or be able to calculate that small change in length really well, which is, you can do that with an extensometer or just decreasing the actual size of the sample that we tested. The extensometer kind of is more complicated, so we just opted for decreasing the actual size of the sample. And this brings us some pretty cool issues, or benefits rather, because this is the sample place that we're making. Originally, we took the full length here and we cut it into sections like this. Decreasing the sample size means we get double the amount here. And I'll pass these around, but so the interstitial voids that I was talking about earlier are these guys right here, right? And you can see on these samples, as you pass them around, I've labeled the dry spots and any manufacturing defects that come along with it, like ridges. So these are the things we're trying to avoid by adding these polyethylene fibers. I'll also pass around this one that actually is good. It is solid, no voids. Just so you can get a feel with it. You can bend it, just don't try to break it. Good try. If you go to the next pop, well, here, I'll talk about this. So this long strand here is a fiber that goes across the plane. So this jute fabric has two fiber directions, one going up and down, one going across. And these up-down directions go into outer plane and then cross plane here. So that's what provides their strength.
So now I'm going to talk a little bit about what a surfboard truss is, but you can kind of think of it as the skeleton of a surfboard, like meant to support loads across the beam, and these beams are typically running it longitudinally and laterally. So here we can see the three main components of the truss. We have the stringer, we have the ribs, and we have the spars. So the stringer is the main rod going through the entirety of the surfboard. Sometimes it only goes 3/4, and it's supported by these spars that run along with it. And then the ribs run horizontally. And it's supposed to provide strength and rigidity to the surfboard.
So a bit more background research, you have also just kind of two gear patents. They, in the 1950s, they would make actually wooden surfboards a bit more commonly. So just kind of taking ideas from these two different patents, we kind of use them a bit in our design. And then actually currently nowadays, there's a company called Emperor Surf, and they have their website here that they currently make wooden ones, though their weight is an issue that they talk about. But they use a kind of internal truss system, and using this, I kind of took these designs and we created our own ribs from this.
So these were the manufacturing methods that we considered for the truss. I won't bore you with the details, but we did end up going with vacuum bagging because it's inexpensive, it creates great material properties, and it's easy to make. So there were some considerations that had to be made for the development of the deck and the bottom of the board, which is just the top and the bottom, as we explained there in the diagram. And that's because, once again, the rocker provides a curvature to the surfboard. And because we're building on an aluminum plate for the samples, that just wouldn't work, because we need to provide a mold that will be able to support that curvature and shape it. So these were the manufacturing methods that we considered for the deck and the bottom of the surfboard. As you can see, there's two highlighted regions, and that's because we had two winners in this category. We had a 3D printed mold that we considered and a foam mold. However, the 3D printed mold we were kind of had to scratch because we don't have the machinery in order to make a mold that supports a surfboard that's 9.5 feet wide. And so now I'll just kind of go over the vacuum bagging process and how we make these samples. So we start by taping down this non-porous release film. This helps extract the composite after we're done. So we take the edges with this electrical or with this vacuum tape, and then we lay down our matrix layer, which is the resin that we have already degassed by this point. So we'll lay down a layer of the matrix, and then we'll lay down a layer of the reinforcement, which is our jute. And then we'll keep laying down these layers intermediately. So place another layer of matrix, another layer of jute. And then once we've laid down all the reinforcement layers, we'll lay down this porous film that allows the air to permeate. And then we place down these bleeder cloths, and that allows for the excess resin to be soaked up into them. Once this has been done, we'll tape down this little metal insert and then place the vacuum bag over it, and that allows the vacuum to be created.
While talking about the joinery of the truss system, I kind of have three different options here. I have a dowel, we have this cut, and a split ribs. And so looking at just how easy it's going to be to manufacture these, how flexible we want the joints to be flexible, and the specs of them. You see that the middle option cut one there. And to help the joint shapes and stuff, we're going to also use an adhesive. So again, looking at flexibility, looking at how well each of these adhesives sticks to the points, manufacturability, the cost of each of these things, and how environmental friendly each of the adhesives are. And so what we're going to do is we're going to do what we are using for the actual epoxy polyethylene, and we're going to add haloxy, which will increase of the flexibility of the joints. So wall shaping surfboards, again, we're not the most best in this, but with a lot of background research, there's a lot of aspects that can go into changing the different surfboards because there's quite a variety out there. Things like the length, the width, the tail, the nose, the rails, fins, and rocker and bottom contour can all affect how well the board performs. So kind of some aspects of performance, you look at the lift and the drag of the board, the stability and the balance of the board, how well the board itself turns, and what wave size this board is meant for. So when talking about our boards, we specifically do a 9'6" board, because that is what Ken had kind of his standard length and would like. 24 inches long, wide, and 3.2 inches at its thickest point. Also, so the rails, I originally thought it was just you kind of choose one and you go from 50 to like 480. But with talking to Ken, I realized no, it's a transitional thing. So normally you start with a 50-50 in the middle and you transition to something like 80-20 at either the ends. So we have made that design change. We're also going with a rounded nose because it's again kind of what Ken's standard is. And then also I did a bunch of research into rockers and did a common rocker height for the tail and nose of the longboards. A bit here, we have the Pew matrix for the tails. So you have 4 different designs here. You have square and squash, round, shallow and fish, and pin. Looking at performance of each of these, how well it is to manufacture these, ease of control, and also what Ken, our sponsor, does. You see that the pin wins out here.
So now that we've discussed and made some decisions, we will continue making decisions throughout this presentation, but we would like to make a prototype to refine our design. There's going to be a scaled prototype eventually, but there's also a prototype that we simulate so that we can run tests on it to make sure that it is working before we try to build it.
So here is our current CAD model. You see on the left there's the full model with all the components on it. And then on the right, there is just the internal truss system there.
So next is doing FEA on the board. And if you don't know what FEA stands for, it's finite element analysis. And it essentially can give us outputting strains, stresses, displacements on the board. If someone were to step on it and ride it, you apply a load and a computational software outputs how the material is going to react. So we can use this to predict if our board is going to be strong enough and rideable before we even make it through the use of those CAD models you just saw. So I considered a few different softwares to do this computation in. Ultimately, it came down to our budget. These softwares are very expensive. And as students here, we only have access to ANSYS and SolidWorks. And ANSYS is more capable of handling composites. So that was my decision there. A few analyses I've done up to this point is helping determine what rib design we want to use. So these were 4 options that we considered. And I applied just a simple twisting torsion to them each in this computational software. And we could see how they each reacted differently. All of these are the same amount of material and the same weight. So we could really focus on the strength to weight ratio of each of these designs. As you can see in the top here, this one had the lowest resulting stress out of all of them. So ultimately that helped us in our decision for what shape we wanted to go with. A few things we also considered were the ease of manufacturing these and the aesthetics of them. When you think about it, it's easier to cut out a circle on a plate than a square. So that was something we considered as well. And again, ultimately, we chose this design with the big circular holes, and that is our final rib design shown there. So something that's really important with FEA is validating our results. It's great you can throw a couple of things into the software and get a number out, but is that number good? Is that number accurate? And especially with composites, they are very complex and have different properties in different directions. So we want to be sure we're accounting for that correctly. So in ANSYS, I just took a simple plate and applied a simple arbitrary load to it and see, I got those results there to see the strain in the Y direction, how it responded. And that value is shown there. Next, through our composites course here at MSOE, we learned a computational procedure. You don't need to know all the ins and outs of it, but you just need to know you can put in the same material properties, the same dimensions, the same loads and everything, and you get output resulting strains. I could then compare these 2 values and prove that our ANSYS simulation is running exactly as it should. We have less than a 1% error between the two calculations. And this tells us when we get to the larger scale surfboard and we simulate someone stepping on it or the board twisting under the motion of someone surfing, that the response, the stresses we get can tell us if the board is going to fail or be strong enough to ride.
Now that we've discussed all these decisions we're making, what our prototype might look like, eventually we will improve the design where there are challenge areas, as there are some to come, I'm sure. And then we will execute the design that we have decided on. So next I'll talk a little bit about our budget. We have about 1,500 for our budget. On my side here, these are the costs that we've already spent. So what we've already paid for. And on the far side, you can see what we think our projected costs will be. Is mainly materials and anything miscellaneous that may go wrong that we cannot predict. So looking into the future of our timeline, we would like to finish making all the samples that were passed around, the different layers to be able to compile properties that we think will work best in the different areas. And we are hoping to have this completed by January 29th. We are then going to test these samples and determine the properties, and we're hoping to have all of those properties by February 14th. We are going to use these properties then in FEA, as we have shown before, and have this refinement done by February 24th. And then we'd like to make a scaled model, a smaller model that we can just look at and refine truss design and any hiccups we might have before making a larger scale. We're hoping to have the scaled design done by March 6th. And then we will be making a full-scale surfboard to be able to go test out in the water, which we're hoping to have done by April 15th. So as I discussed before, greenhouse surfboards really wants to be eco-friendly. This is our main mission and goal. So what's our sustainability right now? How does it compare to what's already happening? Currently, our boards have a foam core, as mentioned. This foam core is in every single surfboard. You need a foam core for every single one that you produce. And not only with this foam core, they don't just come cored. You can't just get it out like that. So you have to shape this core for every type of surfboard that you want, which also produce foam waste. So it's not eco-friendly. It takes up to about 500 years just to decompose this foam. Now, composite boards, while they look better, they may or may not be. So the waste generated from the composite board, as you can see here, along with the vacuum bag over and the tape for it, it looks like quite a bit. And you can't reuse it. We have to do this for every single sample. So it's about 144% of the weight of the weight the waste is compared to what we get of a composite. So looking at a couple options, we did discuss that our mold is going to be made out of foam, but that foam isn't going to be stuck and had to be remade every single time. It's going to be a mold that is reusable. And as we mentioned before, you can have a 3D design printed, which is then again not cloth. There are also reusable vacuum bags, which we cannot afford currently for our project. It will be an initial cost that might be something to invest in. But that's our comparison for sustainability. The epoxy in here is biodegradable, so it should be gone before our foam is. We'd like to give a big thanks to Dr. Ken Cole for being here and being our motivation and inspiration behind what we're doing, and Dr. Kevin Hart for being our advisor. Any questions?
All right, thank you. Okay, we'll move to questions. Committee plus Ken first, and then we'll open to general audience. Committee plus Ken.
I can go. Yeah, I think you had a really clean presentation, so like somewhere behind it, thought that went into a lot of experimental testing. Just had a couple questions. Your one, I know a big part of the constraint was it being biodegradable. And I just want to understand more clearly, because you still are using a jute epoxy composite, right? I believe that still takes quite a long time to decompose. And so I was wondering if there was an aspect that I was missing with regard to how your design is more biodegradable than standard fiberglass base sheet.
I'll take this. So, fiberglass, is not, it doesn't really like break down. So like, soaks up water, right? It's very absorbent. When it does that, it'll expand inside the epoxy, right? So far as the epoxy is covering it, it won't have water in it. But like if this surfboard were to break, we made it out of this epoxy composite, these fibers would expand and it would break up the epoxy more, right? So that will help it break down further rather than a fiberglass, which fiberglass doesn't absorb water. It's all just glass tubes, right? And those are not absorbent or hydrophobic. This is hydrophilic. So that helps it break down more. Okay, that answers.
That's great. And I was curious, I really liked the part about how you used polyethylene fibers to fill the voids in the cotton bags. I always been curious about how coarse the weave looked in those. Is it an option to use a tighter weave for your base sheet?
So, I talked about this with my advisor, Dr. Hart. We could, dependent on the type of weave you get, it could be too thick. Like can we go back to that picture of the in-between the layers? I know it's far back, but so dependent on how thick the individual fibers are, it can create what's known as delamination, where the epoxy, this is delamination right here, right? Where the epoxy and the individual.
I gotta run for a second. Mike, take over. Okay.
Okay.
The individual fibers, they don't mesh well, right? So like right here, you can see how the epoxy, and then there's epoxy right here, and there's a little bits of epoxy in between. And now if this gets too wide and there's not enough epoxy to hold it together, this is what happens, right? So we could use a tighter weave. It kind of looking around, we could do it, but it would be more likely to delaminate. The other part of this is using actual coffee bags. So these coffee bags that we got from Color Tuba are normally just thrown out, right? So we're trying to increase sustainability by using something that normally would become trash. So.
Very cool. All right, one last thing was one of the last things mentioned, and I was curious about. You mentioned 3D printing. I think I heard that, and I was just curious what aspect of the board is this for the inside, is for the ribs and spars, is for the mold? I was curious what that was for.
It'd be, so you 3D print the mold for the interior, so that would allow you to make the bottom and deck contours
Okay.
and mold it from that. And then you would then be able to reuse that for continual more decks and bottoms.
Okay.
But it would not be in the board itself. It would be just in the molding process.
Okay, so it's, all right, that's why I was, I heard the phone mold.
Instead of foam.
Gotcha.
They're
Gotcha.
a negative imprint, so.
Okay, great. All right, I think you addressed my questions. Dr. Cole,
I mean, first off, kudos to all of you. This is amazing to see. And I think from what I've seen, what I know already, this composite will be strong enough and will work. My questions are more about the board itself and what's sustainable and what's not sustainable. So you raised a good point about 144%, correct? Is waste compared to the composite board itself.
So there's about 46 gram, 64 gram composite produces about 144 grams of waste.
Okay. No, just because when you look at the foam board compared to this board, there's a part of me that's looking at that and I'm thinking, which of those two is more sustainable? I mean, this one looks better, it's using natural like materials, but at the end of the day, and I think I said this earlier, like you have this pile of stuff. So are there other ways, just curious, of making that composite that would cost less and might have a smaller footprint, but maybe aren't as strong, but still be comfortable enough to, you know, like survive.
Do you want to say, I'll take it.
So I think Sydney mentioned that we are planning on using or are capable of using reusable vacuum bags, and obviously that would reduce one of the components of this process. Because you would pretty much just attach it at the end and then reapply it for the next one. Once the mold is built, obviously, we'll be able to reuse that as many times as we want to make as many surfboards as we want. As far as the components inside the vacuum, the bleeder cloth is sort of necessary because we have to suck up that extra resin. So it's not really something we can get rid of. And the porous and non-porous release films are important for the extraction of the composite and that sort of that finish at the end. In terms of other processes that we can consider, do you want to go back to just the
We're gonna try to keep it brief. We're a little over time.
right? Yeah, so in all of these cases, we kind of sort of have to have these components in the produced way. So I guess in short answer, for this process specifically, the only thing that we can sort of consider right now would be the vacuum bag.
Okay, we gotta move on. So thank you, guys. All right, next victims. Oh, yeah. You need another sheet, Ken?
Okay.
Here, just.
Yeah, but thing. Did it touch you, didn't you?
Yeah, if you do the thing, sometimes they're gonna. Oh, there's something. Oh, there you go. Okay.
And I warned this to the other team, but try to stay close to the screen when you talk if you can.
I'm gonna try to keep it so I can.
Yeah, I mean, obviously you want to keep the presentation.
Yeah.
You guys ready? Okay. We'll continue this session now with the second talk in the session. We have another surfboard team. They have a slightly different way that they're going to make the board, so I'll let them go ahead and take a look.
Hi, we are taking a slightly different approach to a sustainable surfboard. My name is Sabrina.
My name is Jack.
I'm Owen.
And I'm Jameson.
And our project advisor is Professor Severe.
And some background on current surfboard manufacturing. There's three main components to surfboards, which are the core material, stringers, and the outer shell. First, the core material traditionally has been polyurethane, which is the easy foam that shapes easily, and it's pretty cheap, which would be really just the big portions. But unfortunately, that is toxic. And so with that, they moved to polystyrene, which is a more biodegradable option. Well, not biodegradable, it's non-toxic. But it's hard to shape and it's more dense. And then from that, they developed expanded polystyrene, which is the same material, just expanded, which is the cheap styrofoam coolers that you'll see at the stores. So when they start to flake, they come off usually in little balls, so it doesn't make for good shaping. And that's difficult. And then there are moving on to stringers, which would be this middle portion. Usually they have between 1 and 3, depending on how much support the inner core needs. And these are usually made of balsa wood or other low density woods. And lastly, the outer shell, we get to right here, coats the whole thing. There is a top layer and a bottom layer. Depending on the strength, you can have a 4-ounce weave or a 6-ounce weave on top. And then adds, usually they're fiberglass, but they can be substitute the E-glass for S-glass, and that adds ductility a little bit more to to show.
So with that being said, a lot of these components that we just talked about are not biodegradable. And that kind of goes against the culture of surfing. Surfing is all about like getting closer to nature and being like one with the earth and stuff. So a lot of like even the biggest name in surfing, Kelly Slater, is calling for more sustainability. He wants people to examine like different ways that companies can incorporate the environment into their design process. And so this is kind of something that we're trying to solve here is we're trying to incorporate more sustainable materials, bio-friendly, eco-friendly materials into our designs.
So the inspiration for our project is Greenhouse Surfboards, which is ran by Dr. Ken Cole, who's here with us today. Dr. Cole he noticed a problem with the sustainability of normal surfboards and took it upon himself to work on developing a more biodegradable, eco-friendly surfboard. He's based in Milwaukee, and the goal for the surfboards is to come up with a eco-friendly surfboard that not only balances the craft of making a surfboard look how a surfboard should look and the sustainability.
So that's where we come in. We'd like to help Dr. Ken Cole achieve his goals. We also introduce the waste and the carbon footprint of surfboard manufacturing, as we talked about, does not align with surfing culture and creates a large amount of waste both during and after surfboard lifespan. We'd like to create a traditionally shaped surfboard that reduces the waste and carbon footprint of both the manufacturing and pre and end life cycle. We've designed in and out of scope for this project. In scope for this project would be selecting the materials that we'll be using for the surfboard. We'll get into that a little bit later about the materials that we're looking at. We'd also conduct prototyping, which we'll also talk a little bit about for testing and for deliverables at the end. We'll be experimenting with some of the prototypes that we make and determining the validity of that through data analysis. And then at the end, we'd like to make a recommendation to Dr. Ken Cole about how to proceed with the results that we've developed. Out of scope would be developing a new material or composite. We quickly determined that this would be a good place for something like that, but with our skill set and our timeline, that is not feasible for us. Surfboards have fins. We will not be taking a look at fin creation for this project, and we will also not be scaling this up to a full-scale manufacturing process.
So some of the core materials that we looked at, one of which was mycofoam, which is mycelium based. It's sort of like a mushroom that grows to fill this mold. And it's got comparable, oh yeah, we actually have some of the mycofoam here with us today. We'll pass it around, you guys can take a look at it, but it's similar properties to like standard foam used in surfboards. But it's biodegradable and it's based on mushrooms. Another material we looked at was expanded black cork. This secretes its own resin, which kind of helps with waterproofing, so it's less susceptible to water damage than just typical foams. And it also like made in a mold, but it's expanded to fill that mold. It's a bit stronger but heavier than regular foams. We also looked at we saw some other college student developed a seaweed derived foam. Where he mashed up seaweed and put in some other magic ingredients. There's not much info on that, what those ingredients are, but yeah, it's and he made a surfboard out of it, and that was pretty cool. We also looked at lemongrass. It's kind of a similar thing where it's light and got foam-like properties when it's cured.
So in our background research, we obviously looked at stuff that we could put on the interior for the trusses and everything else, so the ribs. And we obviously wanted something biodegradable, but just in the research, we found three main things. To start with, we found 3D printed or PLA, but it can't be any type of 3D printed structure. Like the image on the top right there, you can have obviously very interesting designs, make the board look super cool, but most of the time you see a hexagonal pattern, which you also see in the aluminum. And that's just because the strength of hexagonal patterns versus the actual volume that they take up, it's a really good ratio. But the benefits of 3D printed material is sometimes it can be recycled. As much as you hear like, oh, it's all recycled material, a lot of times it's like maybe 10 to 30% recycled. The other types of supports we saw were wooden, and that's mainly for the stringers and then also the ribs. As the other group talked about, the stringers go the entire length of the board. And as Owen said earlier, there's about 1 to 3 depending on rigidity and stiffness of the board you need. And the ribs go the width of the board, and there's obviously a little bit more. And the benefits of the wood is that it is a natural resource, so it's not hurting the environment when it gets broken. And then finally, the aluminum, as I said, they used a hexagonal pattern. And this is the strongest material because it is metal, so it obviously doesn't have to worry about breaking too much, or it takes a lot more to break aluminum than PLA or wood.
So some of the outer shell materials we were considering, we considered aluminum. At the start, we tried to use super thin sheets to keep that weight way down. But this can, for us at least, manufacturing wise, that's like difficult for us to create and seal and make a surfboard shape out of that. We are also looking to fiberglass since the core of our material or of our design would be biodegradable. It's technically greener, and so we could use fiberglass to kind of make sure it's strong enough. This is traditional. This is the traditional way that surfboards are made, and it's easy to use and kind of cheap. We also want to look at natural fiber composites like hemp fiber or volcanic basalt. These may be weaker, but if we have a good enough truss structure and our core is strong enough, we think that that'll make up for any lackings that a natural fiber composite has.
Through our brainstorming process, we came up with like 8 main designs, and to narrow that down to things that may be more feasible for us and things we'd like to move forward with, we used 5 main constraints in down selecting. Each of them weighted with the number in the parentheses. And for environmental impact, what that meant to us was the sustainability of the materials used, the print and waste produced by the manufacturing process, and the shipping of the materials to where we were doing the manufacturing, and the end of life cycle. So like whether that the materials that we use in the surfboard are recyclable or biodegradable at the end of life. The second criteria we used was specific strength. That is the strength to weight ratio. The standard surfboard, the EPS foam and fiberglass surfboard has a very high specific strength to weight ratio, and we would like to achieve something similar if possible for us. So that was also rated highest at a 3. Costs, we know through our research that eco-friendly boards tend to cost more than the standard EPS foam fiberglass board. That's because as we're looking at sustainability, those boards do tend to weigh a little bit more, so that increases the cost as well as the materials used in there. And while we're comparing costs, we're only comparing to other eco boards, not to the EPS foam boards. Durability, it has to be assumed that the surfboard will function like a normal surfboard. So when we are discussing durability for us, that means like UV resistance as the surfboard is out in the sun. Its capability to remain waterproof, as the eco materials tend to have less water resistance than the non-eco materials. And then our manufacturability, for us, that means how easy is it to manufacture, the number of materials and tools required to have it be manufactured, and can we as college students with the tools that are available to us and our skill set be able to manufacture this surfboard. We also have a goal of like having that be more hands-on for surfers. It's really big in surfing culture for surfers to shape their own boards, and we'd like to have a little bit of that hands-on for the surfer as well, that personal touch.
All right, so talking about how we kind of came down to the designs that we are looking at and are going to test. As Sabrina said, we had originally 8 different designs that each of us came up with 2. And after going through a design matrix, we got that down to 3. And sadly, a couple weeks ago, we kind of just talking about it, we're like we're kind of just like making something just to say, oh, we made something new. So we thought of different ways that we could probably come at this project. And we thought of, or we were talking to, just talking to each other. We thought that maybe we could look at surfboards that are already designed, that they're already being made, manufactured, written, and trying to find a way that they can be more green. So in terms, we're doing something new, but we're just looking at what's already out there. So for this one, I guess for our two designs that we came down to after the second design matrix, we're gonna go with the microfoam, as we said, and we have the example to pass around. Then the difference is we're gonna look at two different supports. One, we're gonna look at a 3D printed support, which, as I talked about earlier, it is recyclable, quote unquote. And then it is also pretty easy to get a hands on because we do have 3D printers here at MSOE. But it is a little more expensive, and it's obviously not as eco-friendly as our other option, which is just a wooden support. And it's super easy to manufacture, and it's also cheaper than PLA. So we're looking at a supports of wood or 3D printed with an interior of microfoam. And so just to give a little bit of background on why microfoam was the number one that we're looking at, between the two different design matrices we used, all the designs that we had that had the microfoam all scored very highly. And that's because the environmental impact is extremely low, because microfoam is a mushroom-based material that can prolong, can't do the word, sorry. After prolonged exposure to water, it does just degrade because it's just mushrooms that gets treated so it stops growing. It also has a very strong strength, or specific strength, due to its super lightweight but not too dense material. But the reason that we need a stringer is because the compressive strength of the mycelium is on the lower side of what you'll see in standard surfboards right now. It is also very durable just because it is a foam, and once it's wrapped in whatever the exterior casing we're going to go with, it's going to have that added rigidity. And then it's also pretty easy to manufacture, saying that you can buy your own grow kits, and it takes about 8 to 12 days to grow, and it does just grow to the mold.
That original.
Oh, sorry. Yes, that originally received a low score because it was in an aluminum sandwich material. And as Jack said earlier, the aluminum for us college students is not going to be easy to buy or produce and have it be waterproof and keep the mycelium from getting wet.
So next semester, the plan for next semester is to start with some simulation, like FEA analysis and things like that, and design some experiments to do on our prototypes. Once we have those in mind, we'll develop our prototypes, which will take some time to get the materials in. Once we have those, we can then begin experimenting. Owen will go more into some of the different types of experiments we'll be looking at. Then using those experiments, we'll select a design, one that we like based off the data that we found. And then hopefully we can make maybe not a full scale, but a model at least of a surfboard. And then other deliverables such as, the poster and stuff for our senior design project.
All right. For analysis of the surfboard, we have an FEA model that is modeled as a little test coupon of the center of the board. These sections are to simulate stringers and ribs running through the core material. And there will be multiple load cases applied to this test coupon, with one being a bending moment and the other being a dispersed area. The model itself is very able to change the core material, outer shell material, and the stringer rib material along with their thicknesses. And from the simulation, we can get deformation and stress through the part where we can better assign stringer materials and outer shell materials. Once we have physical samples, we can run 3-point bending tests to simulate the wave crashing in the middle of the board, kind of making a cave in and crack in the middle. So this is kind of the setup that we would have. We can also do a rock wall hardness test to find material properties and material hardness of the outer shell or sandwich material. And then we will also be running a compression test to simulate a surfer standing for their feet being dispersing weight. And this can help determine whether the top material in the microfoam will be able to hold up against pressure days. Lastly, there is a peel away coating that we're looking into. It's like a car vinyl where they have like a cutting tape. It's a steel wire that they'll be able to pull through and then have that separate the top and bottom of the shell to separate it from the biodegradable core material.
A lot of our discussion has been focused on the core material and the truss structure that would be internal to the surfboard. That doesn't mean that we haven't thought about the need for waterproofing or the outside shell. Right now, again, that is fiberglass, which adds a lot of the strength to the surfboard. But we would really prefer an eco-friendlier alternative to that, assuming that time allows for it. If our internal structure and internal core material do show to have like strong properties, then we would like to explore other options such as PLA, organic fibers, and bioresins. As Owen mentioned, one idea that we would like to explore, given time allowing, is a peel away PLA coating. Given the correct treatment, PLA can be considered waterproof. So we'd like to coat the surfboard in PLA and then allow the surfer at home to peel away the coating so that it can be disposed of at home without the need to go somewhere else to recycle the materials. Again, if we were to move forward on this path, that would require further testing in addition to the things we talked about on the previous slide. The project will conclude in May. In May, we'd like to deliver design recommendations based on the tests that we've conducted and the testing conditions so that things can be replicated again. And we would really like to present a full scale prototype. We're not sure that we will have time for that, but given that, we'll present a scale model. Are there any questions?
All right, thank you guys. All right, a couple minutes for questions. Committee members first. That's me and Ken. So
Go ahead.
I'll start. Okay. First, what is the degradation timeline for this microfoam? Like if water penetrates into the board somehow, how long is it before it loses its structural integrity? Do you guys have an idea?
No, we couldn't. I guess we didn't look too much into it because we obviously haven't done any testing yet. So that was obviously something that we were going to look at, and probably should have thought about that earlier.
Where'd you get the brick?
You can actually buy these. You can buy just about anything you want in mycelium. Like I said, that it grows super easy. They literally sell like right now because it's winter time. They sell molds for like snowmen and snowflakes.
Is it isotropic?
No.
No, it has directionality.
Not really. It kind of just grows in however, and then it looks like they actually coated the brick with something, but
So-
you don't have to.
So it is isotropic. But does it have the same material properties in all directions?
Yes, sorry.
Yeah.
Okay,
I did the composites fine. I don't need to.
you don't need to worry about isotropic behavior anymore.
In the water question that you just posed, the research that I conducted, it can be like wet and then dried out like a couple times before like degradation like is seen, but if it were like fully saturated in water, like then like that's irreversible.
I'm just thinking about like normal surfboards, and correct me if I'm wrong about this, but like a normal surfboard, sometimes water gets into the belly, right? And will just sit inside the surfboard. Is that correct? Yeah. So you got water sitting inside your board at home and you don't know about it. Your board's sitting there now. There's a polyol of water just eating away at your foam. How long does it take before it degrades? You know, that's probably an important consideration. You know, if a surfboard one day, you know, guy takes the surfboard out for the first time in the summer and half of the foam core is now wilted away, gonna be pretty upset about that, right?
Yeah.
So keep that in mind. Another question is that foam, you know, it's got to be shaped, right? You know, there's some artisanship associated with creating a surfboard. Another thing you didn't really talk about is the shape of your board, which, you know, that's another question maybe Ken will have. But how easy is it to sort of shape that? Like if I took a like sandpaper or whatever, and I rubbed it across that, does it come off easily? Does it flake? Is it something you can shape easily like? foam?
Well, we didn't really think about shaping it as in like cutting it, because like I said, the molds can grow, like, they just have a mold of a brick and they don't have to cut this at all. And it
Okay.
comes out just like the mold, and like I said, the other molds that they have. So we figured we'd make a mold and just.
So you want to create it in that shape?
Yes,
Okay.
because it also gives the surfer like an option on how they want it.
Do you have a plan for how you might make the mold?
We plan on 3D printing the
Okay.
mold and then, yeah, we would like to like explore, also just like, what's the word, like placing like the plastic sheet over and like heating it, like also that is an option.
One last thing I'll say, and then maybe I'll let Ken ask a couple questions, is that we have this new laser cutter downstairs and like SG01 or whatever it is.
Yeah.
And so if you're thinking about maybe using like a stringer, like made out of some light wood, like balsa or whatever,
Yeah.
you can literally go down a laser cutter. It's huge. Put a piece of balsa wood in there and just run the program and it'll cut your truss pieces to whatever size you want, right? That might be really useful for you guys if
Yeah.
you end up going that route. So
Oh, yeah.
end of my comments. Go ahead.
No, I mean, this foam is fascinating. I've been curious about it forever, so, you raise a good point, so my question would be, I would encourage you to scratch that brick up and see what happens.
Yeah, drop that in some water too, like see.
Well, yeah, we
Yeah.
actually got this in what?
I got this in yesterday.
They got it in yesterday after they said they were gonna
Perfect
send it
timing.
back.
Yes.
Yeah,
No, because when you shape foam, if you start off something that's really rough, you're gonna see a bunch of beads fall off.
Yeah.
Then the higher grit you go, it just gets like glass basically, and then you wrap that.
Okay.
What you don't wanna have ideally is really a finished board that has a lot of dimples, so that's a pretty coarse finish. So see if you can shape that down to a very refined shape of rails. Cause a finished surfboard, as you know, ideally is pretty smooth.
Yeah.
I saw reference to basalt as well. Someone mentioned, basalt. Yeah, and I'll just say that I've used that before and I was very impressed with it. So it's something to at least try to track down. I do know it's very difficult to locate.
Okay.
And then the support, you mentioned support. What do you mean by that? Is that just the stringer you're referencing?
Yeah, so because like I said, the microfoam has on the lower side of the compression for foams that are used in surfboards currently. We're thinking of the use of stringers and other ribs, or we're obviously gonna be testing this. We will be figuring out exactly how much we will need. Like, I'm gonna hope that we only need 1 to 2 stringers to actually add the stiffness that we'd like to make sure that there's not pressure dings or that it bends too easy.
In this FEA model, these surfaces can be turned on and off, so we can explore like different rib and spar combinations to get the best properties that we're looking for.
General questions from the audience. Maybe we have time for one, if there's any in the general audience. Sydney, go ahead.
You said that the mushrooms grow and they stop, right?
Once you have to heat treat them and then they stop. So one thing about the molds I found interesting is if you grow your own, you can actually grow parts and then put them together and they will intertwine, like they will like weld if you don't heat treat them. But once you heat treat them, they'll stop growing altogether.
Okay, so it's a heat treat, not like a treatment you can spray on them or anything.
Yeah, it's just you heat them up and it kills like the outermost bacteria. And I believe I don't think it turns into this color, but as we said, we haven't grown it yet, so.
Very cool. Okay, I think we gotta move on in the interest of time. So thanks, guys. Okay, so if you're in a surfboard group,
Sorry.
surfboard groups, please go next door with Pen and have a conversation. I got some questions for you. Well, surfboard groups, go have some chats with Ken next door. You got some time with them.
Nice presentation, JMO.
Sorry, you missed it.
Yeah, no problem. I'll get a few minutes to get to that. All right, next committee of the commission there.
That looks kind of.
All right. Dr. Farrell. Thank you. Take this form. And You're the advisor.
For the second one, not.
Here is your advisor form, here's your committee form. Yeah. Thank you.
Oh, really think about it. I don't play well under the. And let's see what this. Well, are you gonna get well?
Yeah, I think so.
Yeah, I do.
Okay, sweet. Excellent. Now. I don't think that's gonna work on Venus. I mean, I'm just.
Well, hear them out.
It's not a good start.
Hear them out. Still got about 1 minute. We'll let people trickle in if they're still coming to go. You're good, you're set. Bill?
He's not good.
Great.
I'll try not to snore.
Yeah, pretend you're awake.
Everything is still going. My camera is still working. Had some camera issues this morning. It's a little
Oh.
finicky. Right, so if you're talking, by the way, gentlemen, try to like be tight on the screen so that you're in the camera view, just so you're aware. We got probably like to Tyler's right hand shoulder on that side and then maybe to Dylan's shoulder on that side. Okay.
So we got somebody coming in at 10.
Okay.
Derek.
Yeah.
In Alabama.
Okay.
Work.
Yep.
Okay.
If you send them a link for the meeting.
They should get, yeah.
Yeah, I'll let them in.
I was confused a little about, because there's 3 of them.
Yeah.
So
There's different links for each of the 3 rooms. So as long as you send them the link to this room.
well.
It was the right room.
The link to the right room. Okay, we should be good.
Okay, so 9:30, so we'll go ahead with the next session. We're gonna switch gears here a little bit in the session. We heard about surfboards for the first 2 talks, but now we're gonna switch to space because space is awesome. So we're gonna hear about the AIAA Space Mission Design Competition. So go ahead, gentlemen, try to keep it to 22 minutes or less. And then we'll have Q&A, so take it away.
All right, the race is on for the AIAA Space Mission Design Competition. The AIAA is the American Institute of Aeronautics and Astronautics. Each year they host a space mission design competition. This year's competition is human-enabled Venus robotic exploration. The competition schedule, since we plan to enter, is to have a proposal entered by February 9th of next year, and then our final proposal by May 12th of next year. So the design process, first we got to start by defining our problem, which we can do by looking at the competition prompt. This year's prompt relates to Venus and how it has a very harsh climate due to its runaway greenhouse effect. Understanding this harsh climate could lead to a better understanding of climate change here on Earth, if I want to understand it. And we want to understand Venus as a system, which means more than one set of measurements, since one set of measurements will not be enough. And we also want to do this by including humans in the loop, the ability to human-controlled craft, so that we can make quick, real-time decisions on doing our experiments. The team's scope of this mission involves the robotic systems. So anything from end to end, so from launch from possibly Earth to deployment and end of life on Venus. What is not included in this is anything really related to the crew portion. So whatever the crew is in orbiting Venus and how it relates to that and how they get there. So from the prompt, we defined our problem statement as the harsh climate and runaway greenhouse history of Venus provides challenges to an interest in its exploration. Potential scientific value from incorporating real-time human decision-making remains unexplored. There's a need to design a robotic science mission for Venus that not only achieves key scientific objectives, but also leverages the advantages of human proximity for advanced scientific return.
So to begin our research, I began looking at the heritage missions, and I wanted to start off talking about the NASA Mariner 2. This is the first successful space mission at all to involve Venus, and it took place from August 1962 to January 1963. It flew by Venus on December 4th, 1962, and passed approximately 34,000 kilometers close to Venus. And you. And then I wanted to talk about a few of the Venera Soviet missions. So first up, we have the Venera Soviet 4. This is the first successful Venera mission. It was the first spacecraft to ever return atmospheric data from a different planet. It found that the atmosphere was composed of 90 to 95% carbon dioxide. And it was crushed at an altitude of approximately 27 kilometers. It found a temperature of 280 degrees Celsius and 2 megapascal pressure of 2 megapascals at the point of being crushed. And lastly, I wanted to talk about the Venera 7. It was the first spacecraft to make it to the surface of Venus. It was parachuting down and the parachute failed and it ended up crash landing on the surface at a velocity of 16.5 meters per second. It transmitted data for 53 minutes, including 20 minutes from the surface, and it found a temperature at the surface of approximately 475 degrees Celsius and a pressure at the surface of 9 megapascal. And a few key takeaways were some conditions to design for, and the high DH ratio in the atmosphere that was found and some granite-like rocks that need an abundance of water to form were found, which could be evidence of water being on Venus in the past. So we just wanted to look into Venus to see how we could learn about climate change in her.
From that, we can make our mission constraints. Some that came from the prompt itself for the overall mission design must stay under $1 billion. The craft must have human in the loop control. The launch date must be no later than December 31st, 2037. Completed, the crewed portion completed no later than December 31st, 2039. And then we want to collect data of Venus as a system relating to its harsh climate, which includes measurements of at least one temperature, pressure, atmospheric composition, or surface composition, in at least 2 locations. And then the operational mission of the crew should last no longer than 30 days. Some objectives we'd like to meet is test for life in the upper atmosphere, return at least a 100-gram soil sample home for further study, return at least a 1 liter of atmospheric sample home for further study, visit the Mons volcanic structures to test lava temperatures, have all equipment sent with the crew portion of the mission. All robotic vehicles survive for at least roughly 1 week.
Right, so because how open-ended this project is, some of the challenge was just coming up with the objectives, which we have listed here. So we rank these based on how well they incorporate human in the loop, their scientific impact, how our probability that we can be successful doing them, and can we design them in time. So based on our ranking, scientific data was our top priority, and bringing back a lava sample would be our lowest priority. And these priorities are reflected in our designs going forward.
So with the objectives made, we can now start to generate concepts. And this is all the concepts we came up with each of us coming up with at least 2 things ranging from atmospheric or things staying flying vehicles to ground vehicles to go and gather surface data. In the end, our robotic system we decided to go with was the VAVA, or Variable Altitude Venus Ascent. It started off as a balloon, but it ended up changing to a more of a blimp design for better control. In total, the overall mission, ideally, we'll have 8 total blimps, 2 as rover carriers to go and get information about the surface, 2 for our function of altitude objectives, 2 to gather atmospheric data, and then 2 to help with communications. Then our primary focus will be on the VAVA design itself.
So to give a rough mission overview, again, so the $1 billion budget that we were given isn't necessarily how much it costs from going from Earth to Venus. That just includes our narrow subsection of the design, basically saying that all of the different entry vehicles, rovers, and probes need to be under $1 billion. Right now, we have a rough range of the payload mass from looking at different research data, saying that we have a range from 500 kilograms to 2,000 kilograms. And then our operational power is about 1 kilowatt per hour with 1 to 2 kilowatts for spiking. So total of 3 kilowatts per hour for the blimps. And then here's just kind of a rough diagram of some of the main objectives. So essentially what we want to do is go from a parking orbit that the crewed mission would be within and deploying with some sort of entry vehicle where we do like a soft landing in the upper atmosphere. And then from there, having the blimps start the scientific objectives by deploying different payloads.
With our design in mind, we can then break it down into subsystems and assign those. So we have Connor on materials and structure, Dominic on propulsion and controls, myself on communications, Dietrich on power, Tyler on normal mechanics, and Dylan main heritage focus.
Right, so materials. Obviously, material selection is going to be really important for any mission on Venus. So I did a lot of background research and just wanted to highlight an interesting one which utilized Glenn's extreme environments rig, which actually created a simulated Venus atmosphere to test materials and how they react. So in the table on the left, there's some of the constituents of the near surface atmosphere, which is primarily carbon dioxide, but also includes some more hostile chemicals. And on the table on the right, a lot of candidate materials and how they reacted to this environment. A lot of them not ideal, so material selection is of course very critical here. In addition to this, I also looked into the effect of atomic oxygen in the upper atmosphere and how it's amplified with the heat of the atmosphere, and as well as solid lubricants. So some constraints with the materials, because we're in the upper atmosphere, it's not quite as severe in the Vava. So the materials need to withstand 200 degrees Celsius, and they must survive the duration of the mission in the atmosphere, including the sulfuric acid clouds. Our objectives is they should be strong and lightweight to enable efficient operation. So I've made a list of candidate materials, including titanium, aluminum, some carbon fiber composites, and stainless steel. I rank these based on their specific strength, their chemical resistance, their manufacturability, and their coefficient of thermal expansion. With this weighting, carbon fiber epoxy was my highest scoring material, but in a close second was the titanium alloy, which going forward we will use as the primary structural material, just because we can be a little more confident in a titanium alloy over a composite because of some of the complications with a composite that isn't really considered in this matrix here.
Right. Morning, my name is Dominic. I was in charge of the propulsion for this project. I decided to start with a research basis and determine essentially what sort of propulsion we need, what would takeoff look like, the various types of propulsion that we need. And so essentially what we decided was that takeoff itself wouldn't be horizontal or vertical because we'd essentially be leaving atmosphere. And so therefore the craft would be landing in atmosphere. So therefore this sort of gets rid of the whole need for orientation of takeoff. We also determined that among the propulsion types we'd like to use, propellers for at least in atmosphere travel are ideal for our blimp design, and potentially even sort of either chemical or electric propulsion to get us in and out of atmosphere. So my research basis for this semester was largely in chemical propulsion. So I hate to say worst case scenario, more complex scenario essentially is what it is in getting our design idea from the ground up to the atmosphere. So some fuels research that I did was into green monopropellants and determining what would be a less toxic and yet a more efficient way to propel our vehicle. And the one that stood out the most from Nasir et al.'s research was liquid nitrous oxide monopropellants, which is essentially a catch-all for nitrous oxides, nitrous oxide propellants, and anything that uses sort of nitro compounds, nitrous compounds. This then brings us energetic ionic liquids, which are salinized aqueous solutions mixed with fuel and then combusted. And this brings us again to hydrazine, the traditional rocketry fuel used in most of our heritage missions discovered or discussed. And then hydrogen peroxide aqueous solutions was less efficient and is recommended more for low to mid thrust scenarios. So, for example, it might be rather nice to use for yaw and pitch, or essentially steering our vehicle while in atmosphere. Hybrid rockets research, this brings us to the use of using solid fuel and liquid or gaseous oxidizers, as they are smaller and more throttable than solid rockets and liquid rockets as well. And there's a greater flexibility in the rocket design and also greater throttlability. And so I took a look into Ju Bok Young's hybrid rocket design, where he used a solid spiral shaped core which would influence any of our decisions should we decide to go with chemical propulsion. And so the next steps for propulsion are to decide whether we're using that chemical propulsion or the electric propulsion to get us in and out of atmosphere. That'd be either for our blimp or for the entry-exit vehicle. And selecting propellers for the in-atmosphere travel is also going to be necessary, which means I've got to pick up motors, gears, propellers, not just for moving the thing forward, but also for steering the thing. And also, no matter whether we go with chemical or electric propulsion, there's going to be a propulsion diagram that I'm going to generate, which will include our tanks, our pipes, and our necessary valves. Next, we have communications. So the main goal of communications is trying to provide real-time audio, visuals, and controls for the humans in the loop. So this would be under a 10-second delay. And also having near real-time data return. So that way, if there's a mistake on some measurement, they have the ability to rerun that. So also 10-second delay maximum for that. And then ability to have communication between all robotic systems, since we're wanting to have multiple lava limbs. So the first thing to look at is Venus is a very differing atmosphere from Earth. So looking at how that changes our signal being sent through. The graph on the right shows the attenuation on the y-axis versus the altitude as you get closer to Venus's surface and how it affects there. There isn't much attenuation, but there is some due to the sulfur dioxide and sulfuric acid clouds on Venus. The small attenuation will result in a little power increase needed to be able to send the signal. And then this graph also focuses on using S-band frequency, which is 2 to 4 gigahertz. And sticking at the lower frequencies, we can use things like Wi-Fi frequency of 2.4 gigahertz, which already has lots of prior made technology for it. Then next we have the communications power budget. So we know what we want to get back from what we're sending. So starting with the Shannon-Hartley theorem, it relates the data we want to get back as the capacity or bits per second being sent, B, the bandwidth that it's being sent over relating to its frequency, and SNR, the signal to noise ratio, which is our radio frequency system. So looking at like the Mars rover and how that functions, it ran off of 256 kilobits per second for sending its data rate to a satellite, I believe Odysseus satellite orbiting Mars. And then for audio and visuals commonly used for 720p, 3 megabit per second will work for that. And then using a frequency of 2.4 gigahertz will provide plenty of bandwidth for all of this, which means we can use lots of already pre-made things for Wi-Fi. And then that leads to the power budget equation, PR being the power received, which is kind of fixed into how much power needs to be returned so that we can actually get the data out of our signal. And then we can mess with epsilon, which relates to our losses. And the main thing we can mess with there is what type of antenna we're using. And to more directive antennas lead to a higher gain value, which results in less power being needed. And then we can figure out how much transmitted power we need to be able to send our signal.
I'm Dietrich Fair, and I'm responsible for the power subsection. The main things that I had to do was to define power generation and power storage. These are two different things that vary in the fact that for power generation, I'm answering the question of how do we produce electricity for our craft. And for power storage, I'm answering the question of what do we do with any extra electricity we have and how can we use that for later use in the mission. To start off, I came up with some estimated loads for our system. These included what I consider continuous operation loads and then the occasional power spikes. For continuous operation, that'll be things like basic communication, video feed, pictures, things like that. I estimated about 1 kilowatt for that. Anything with basic sensors, the power draw for that was so low that I'm considering that negligible. The occasional power spikes, that'll include things such as propulsion control, any imaging equipment and chemical analysis equipment that we want to use, and then any deployment of probes and our communication with that. I'm estimating an extra 1 to 2 kilowatts for those occasional spikes. And this leads to our general objectives and constraints. Starting off with what the power system needs to do, it needs to be able to sustain continuous operation of 1 kilowatt for that continuous operation. And then it needs to be able to handle the power spikes that'll add an extra 1 to 2 kilowatts for about 8 hours at a time. For the objectives, we would like to provide 3 kilowatts of power during the Venusian day, and then we would like to store energy for 24 hours of continuous operation without any need for the power generation. So the main things I looked at was solar and wind and radioisotope thermoelectric generators, or RTGs for short. I mainly chose to look at solar because over here we have solar flux from the various Soviet probes. As you can see, at around 50 kilometers, which is where the mid lower clouds are, the solar flux increases drastically. Because we plan to operate above this cloud level and occasionally dipping into the cloud level, solar is going to be a quite viable option. For wind, it's a little bit hard to see, but the curve over here is the wind data from various Pioneer missions. Where we plan to be, it's going to be pretty fast winds, between 40 and 60 meters per second. And then the radioisotope thermoelectric generators, I decided to look at that because they produce reliable power used in heritage missions before. When comparing all of these, solar was the cheapest per watt and it produced the most power per kilogram. I ended up looking at the cost, power output, and reliability. Solar ended up winning at 2.6. For batteries, it really depends where you want to go. That'll determine what type of battery you want to use. For a surface mission, because the temperatures are so high, NASA's been developing molten salt batteries. But because we're focusing on the aerial mission aspect of this, traditional batteries like lithium-ion batteries will be just fine. So these are the current design ideas that I've come up with. I'd like to use thin film solar cells because we can put that on top of our blimp. They're light, they're thin, flexible, and they still produce a decent amount of power. I'm thinking we'd want between 1.5 and 2.5 kilowatts for that. For batteries, I found this Eagle Pitcher electric vehicle battery that can be used on aircraft. It has 1.26 kilowatt hours of storage. The only problem is that it is quite heavy. So in order to satisfy the 24-hour continuous operation requirement, we would need 19 of these, which is quite heavy at 323 kilograms. This is why I'll need to do some continued research to maybe find a lighter battery or maybe re-clarify some of those constraints. For our general system, I'd like to have the generator or the solar cells 28 volts and then have the 24-volt DC power supply. I found that this was quite common in other aerospace applications, for instance, satellite bus systems produced by Boeing. For my next steps, I would like to clarify the batteries, solar panels, and their quantities. I'd like to develop a thermal system to keep all of our electronics at a comfortable temperature. I'll create some wiring diagrams, do some Simulink modeling to figure out how our system will respond, and then figure out how long it takes for these materials to degrade to try and figure out what our post-mission lifespan might be.
Morning, my name is Tyler Bernstein. I was responsible for the astrodynamics and orbital mechanics for the mission. I approached the problem, basically, I didn't really have a good background in orbital mechanics, so my advisor suggested Pressing Economy's 1993 orbital mechanics textbook. From there, I learned a lot and I gave a really good background to a lot of the different math and applied mechanics behind orbital mechanics. Being that there's a lot of math, I really wanted to stay out of the weeds, and you can see on the right there is a generated plot of a parking orbit that I ended up making. That helped give me some relational speeds and helped us figure out that, hey, we're moving really, really fast and maybe deploying the balloon at 7 kilometers per second isn't viable. I also researched and talked to professionals. I reached out to a few people at JPL, Dr. Hall being one, another being our Dr. Farrow here on campus, who helped really kind of get me out of some of the weeds and help me clarify how we're going to actually approach the mission. Moving into our objectives and constraints, the objectives for the mission, again, based on the AIAA prompt, we are not able to launch the mission no later than 2037. The completion of the crewed operation should be no later than December 31st of 2039. Allowed for human in the loop direction and operations of directional maneuvers. For objectives, the designs of the spacecraft and the orbital path should be ensured to cover optimal target area, maximizing observations and operational capabilities, prioritizing fuel efficiency and orbital maneuvers to extend operational lifespan of the spacecraft, and then designing for robustness, making sure that the actual spacecraft can handle all the minor deviations without compromising mission objectives. From here, I plan on approaching it by using orbital determination, again, tracking from the actual manned group that is in parking orbit, sending signals back and forth to them to make sure that, hey, we know where we are and where we're going. And then again, understanding all the different perturbations that would be going or that the robot would encounter throughout the lifespan of the mission. From there, the actual transitional plan is starting from that parking orbit, deploying it using some sort of inflatable decelerator from that parking orbit to get us into an above cloud cover orbit. From there, stabilizing our path, making sure that we can get all of our scientific objectives and drop payloads where we would like. And then returning some portion of the robotic system to the crewed orbit for returning atmospheric samples or soil samples.
About 1 minute.
Path moving forward, I plan on using governing equations to really grab at the limiting factors of the deployment, making sure that we have enough volume in our blend and enough delta V coming into our actual atmosphere. Planning the mission around the actual sun's hail cycle trends, and then for actual implementation of all the different math using MATLAB Simulink Aerospace Toolbox for all the different modeling of orbital mechanic transitions, and then collaborating with other team members to determine viable options for that sample recovery.
So this leaves us where we are in the design process of developing solutions. So we will continue with our research and design of building solutions. Some other important dates coming up are February 9th again for us to have our proposal submitted to the AIAA to formally enter the competition. And then May 12th as to when we have to have our final proposal submitted. Brings us to Q&A.
Okay, thanks, guys. All right, we'll move to Q&A, committee members first, and then general audience, maybe just time for a couple questions.
How many hours do we have?
About 168.
I'm sorry, question or
I'll start with a question. This is massive. I don't know how.
Go ahead.
Wrap your minds around it.
You've blown Swedish as wrong.
So the end objective in May is just a basically concept.
Yes, it's a mission design concept.
Okay.
Unless you happen to have $1 billion sitting around.
But I mean, you're not designing the, you're not putting the Goodyear on the side of the
No.
sort of thing. So basic, I'll try to do basic questions. One is, this blimp is presumably going to be flexible.
Yes, to an extent.
So what material would that be? I mean, you talked about titanium carbon fiber, but what material would you use for something that's got to be flexible and handle the temperature excursion?
Come to the middle.
Yeah, we did. So originally, like, a lot of our process was coming up with the idea. We had originally sort of a balloon rather than a balloon. I was focused more on the underside structure of that balloon. Tyler had some ideas of the material the balloon was made out of, but
There's some PTFE woven fibers that are decent, but we haven't done too much research, and I don't want to lead you the wrong way. We're not super sure at this moment. We've looked into some options, but we're not.
Okay, are you going to need to specify that by May?
Yes.
So that is something you can do.
Absolutely.
My last question, and then I'll stop, is when this thing is deployed, is it in orbit? Is it flying around in the atmosphere? From a modeling standpoint, what is it doing?
It's more or less flying in the atmosphere. It's being a blimp. Where our target range is 50 kilometers to 70 kilometers above surface. So if that lands us in a hovering orbit, or I don't know how you want to define that, we're not going to be orbiting like the ISS where we're going 16 minutes or something every orbital period.
I guess what I'm getting at is where is this thing going to be with relation to your crew vehicle, which is in orbit?
Yeah, more or less atmosphere, upper atmosphere.
So it's tooling around in the upper atmosphere, but in communication with the orbiter.
Yeah.
Okay, I just wanted to make that clear, whether you're flying it or sending it in an orbit or exactly what's going on.
Absolutely.
Thank you. Maybe Bill, you have time for one question, then we gotta move on.
Oh, sure. So the first question I had, so Professor Swedish already hit, which was your materials. You discussed all the rigid materials, but you never got into the flexible stuff. The next one was a concern with your thoughts about antenna. So you were looking at trying to optimize power for all of that, and you were looking at directed energy antennas. But if you're in a blimp floating in the atmosphere, you're gonna have to supply energy to actively steer that antenna continuously, keep the link working. So you've got to bring that into your energy calculation. How much is that gonna take? All those actuators and so on. Let's see, next comment that I had, so wind, I'm glad to see that you ruled wind out, but I think it would have ruled out much quicker if you realized that you had to have a differential across your blades, and if you're moving with the atmosphere, getting that differential is really difficult.
Thank you for bringing that.
And then,
That's one of mine.
the other thing was, you had a 10 light second distance delay between your human and your thing as your farthest distance. Is that looking at, as the orbiting capsule is going around and your blimp's down here, it's going like to the extreme horizons on the planet or something? How did you come up with that 10 light seconds?
So that overall is it would be from the people in orbit down to whatever probes we'd have on the surface.
Okay.
That's where I got that 10 seconds from. That would be like maximum worst case scenario type thing.
Okay. Because one thing to do would be to convert that from a time delay to a distance. And that's a pretty easy calculation with speed of light and so on. And then the last one is, I've got my overarching concern is the idea of the integration of all the systems. So you've done a lot of independent stuff, but I don't see any concern for the intercompatibility of all the systems. And that's something that's gonna come back to bite you as you put that final thing together.
More systems engineering.
Yeah, because that's for aerospace projects, it's all about in the front end, looking at the ability for all those systems to connect and work properly, and not like walk all over each other's feet as you're trying to get the final goals accomplished.
Yeah, NASA is pretty much obsessive about that.
So,
But just so you know, that's one of the first things they look at.
but the quick comment is you guys have done a lot to corral together a lot of information quickly, relatively quickly for the skill level you brought into this, not having a full aerospace background in all this stuff. So good job so far. I just gotta clinch it.
Yeah. Okay, thanks, guys. Gotta move on. Okay. Let's get the NASA team up there. NASA space. Rawr.
Guys, it looks like Mike is on.
Yeah, we got a couple
Couple
of guests in here.
Emmy.
Yes. It looks like Griffin, we got your dad maybe in here. There you go. 10.
We should get like signalize.
Countdown.
I didn't bring my phone.
Yeah, a couple of seconds here for the committee members to evaluate the previous.
Yep.
Thank you very much.
We already gave me one.
Oh, I already gave you one. What you get your, yours for the.
I got your license.
Let's give Bill a second here to fill his form out and then we'll start on the next talk, which is the last talk of the session.
Why do we even have that?
The poison for Cusco. The July for Cusco.
It's not an acronym.
Cusco's
It's
poison.
still pretty fun. Yeah, exactly.
Sounds like DST. No, you know that.
Yeah. Here's the acronym.
Thank you very much. Okay. This is the last talk in the session. We have one more space talk, shifting gears a little bit to food storage. So I'll let these guys introduce themselves and take it away. Shoot for 22 minutes and then Q&A at the end.
NASA has asked for a passive food storage system on a deep space train vehicle. The concept is that this vehicle will launch from Earth to a lunar orbiting station where they will have the opportunity to stock before they launch from the lunar orbiting station to Mars or any other deep space journey. The deep space transport vehicle is made up of two modules. It's going to be the habitat module where crew will live and work, and then the logistics module where all the food and other supplies will be stored. So that's where we're focused on in this project. Kind of as I mentioned, the main requirements for this project, we're going to be focused on keeping food within a range of -20 to 0 degrees Celsius. And then ideally, it will be an entirely passive system designed based on the opening and closing of louvers through thermal expansion. And before I get into kind of our main goals for this year, I do want to mention the 3 previous design teams that have worked on this project. They're the ones who did a lot of the base work and a lot of the main proof of core concepts for this project. They're the ones who said, we're able to like simulate and say like, yes, it is feasible to have food stored between -20 and 0 degrees C, and it is possible to do it mainly passive. So where we kind of step into this project is when it comes to like the special cases. We're here to look at what happens when a crew member actually enters the logistics module, whereas in the past, it's kind of been without disturbance. So we're here to see what happens to the food temperature when we have that extra heat addition. And we expect it to be decently cold, obviously, in the logistics module. So also, how long could a crew member even spend in the logistics module? Further, kind of like I was talking about, there is going to be a lunar gateway where this vehicle will dock. A big thing of ours was looking into how the moon affects our radiation network and how that's going to end up affecting our food temperature. And then another big thing is the whole thing works on the opening and closing of louvers. In the past, it's been a single louver on the end cap. So our big question is, best case, how many louvers should there be? How large should they be? And really, where should they be placed?
I'm Griffin. I was in charge of doing the thermal modeling for this project. And one of the things I did was I did the resistance network of inside of the LM to model someone coming into the LM. The other thing that I did was model the radiation outside the LM when it is attached to a lunar gateway orbiting the moon. And basically what we did this semester was create a base model. And then next semester, we're going to be like changing different variables on it and trying to get some more research from it.
And then I'm Zach, and myself and Alyssa were in charge of the MATLAB portion of our project here. The MATLAB portion mainly focused on integrating the radiation model that Griffin made, along with the other past teams' codes, in order to achieve some of the things that Alyssa said earlier. But we'll say more on that.
Then I'm Jordan. Myself and Brandon both worked on the louver actuation system for the module. We were trying to make it completely passive, as Alyssa mentioned. We explored a lot of the previous group's work of utilizing like aluminum rods to thermally expand and contract to open and close the louvers. We also did our own research into bimetallic springs and the possibility of utilizing those, which has been done on like CubeSats and stuff in the past by NASA. And then those would basically just open and close and change the data vector of the louver based on the position relative to this.
Yeah, and the whole thing is a proof of concept, just saying whether we can do this or not for NASA, so that when 10, 15 years in the future, when we decide to do this manned mission to Mars, they know whether or not this is possible.
Okay, so this is a previous year's work, and then there are two different models that they did. They did the rigid and the inflatable model. NASA still doesn't know which model they want to go with for the LM, so they asked us to like model both of them for our project. Is what it is. And then you can sort of see more of what the project is about on this side. So basically, like Alyssa said, there are two modules. There's a living module, and then there's a habitat module, and then there's a logistics module. This is where they're going to store food and all this, and then this is where they go live. So basically, they're going to go into this airlock here, and then they are going to open up this door and then go in here and then get food and come out. So point of this, like what we're doing, is keeping the food in here at a low temperature. So what they did was they did a thermal network from the habitat module all the way over here and out through the heat sink. Because what we're doing is we're designing a passive system. So basically all of the radiation and all the heat is going to go out through here, the heat sink right here, then out into outer space. That's why everything is modeled to down here. And then on the inflatable model, they put the louver on the end cap because basically it's like a big balloon thing. So they put it at the end there. And this was last year's work. And then so this year, one thing we did was modeling someone coming in. So we just opened the door and then did a thermal radiation network through that for both of these. And then we simplified this big circuit to get a single equation, a single resistance. And then we put that in a MATLAB, try and get some data from it. And it should also be noted that in the LM, on the left and right side, depending on where you're taking data from, the resistance network is going to be different. So when you're on the left side, resistor 13 is going to be above resistor 9. When you're on the right side, resistor 9 is going to be above resistor 13. And then in the future, so this next semester, what we're going to look at is putting the heat sink in different places and just sort of playing with some of the variables in this and seeing what sort of information we can get from it. And then this is another thing, this is last year's team, but we still implement it into our design. Basically, they rearrange the circuits in order to get the temperature of the food on two different sides of the food because we want to make sure that both sides are in the desired range. So this is just some of the rearranged models in order to get the temperature of the food inside and out to get a more accurate representation of what the food temperature is and make sure that we're in the desired range for the food temperature. And the other thing that I did was the radiation model. So the radiation deals with everything outside of the LM, like all the heat going out. So last year they modeled the LM when it was orbiting Mars. This year we're going to be attached to a lunar gateway right here. And the lunar gateway is orbiting the moon. So basically we did a 6-body radiation model to try and model all the different things that the heat will hit when it comes out. So instead of doing Mars, we modeled when it's orbiting the moon and the different radiation from that. And then this next semester, what we're going to be doing is looking at how different louvers are going to be affecting the radiation model, like what will happen if we have 3 different louvers on the end instead of just one. And this was just basically some of the base models that we got for this thermal model.
So when it comes to the simulation that past teams have created, kind of like I was saying originally, they were able to provide a proof of concept, but they also did a lot of other work into other factors in the LM. So if we look at these top 2 plots, these are kind of showing food temperature versus position in the LM over different angles of theta, so different angles of the louver. And we can kind of see that they were able to prove that at the door, that's this top blue line, the food is always going to be within temperature. If the food is in the middle of the logistics module, it's pretty much always within temperature. But then at the end of the logistics module, if it's near the cap, at some point, it's going to become too cold if the louvers are opened all the way. A lot of the other work they looked into They did some work into like the sensitivity of the system, kind of looking at this down here, just a basic relationship between louver angle and food temperature, and we can kind of see that it's a very steep curve. So at some point, the system is like sensitive, and when it is initially, when the louvers are initially opened, but as they get to like about 80 degrees to 180 degrees, there's very little temperature change with that. Another big thing they were focused on kind of comes in with transients. A full transient model is a little too complicated for the course of a year. So our team and previous teams work on a pseudo transient model, but kind of what the past teams were able to do to make it as close to transient as possible is by like altering the habitat module temperatures and testing for all these other like variables in there. A final thing the last team really focused on, I think this part right here, is the temperature gradient inside the logistics module, where having a single louver on the end cap creates this gradient between where food is going to be stored.
All right, when it comes to our current work that we've done on the simulation model, first and foremost, it was a large challenge to try to reverse engineer the past team's code. It took us a lot longer than had been anticipated. And as you could expect, yeah, sifting through 1,000+ lines of code you didn't write, it's very difficult. So we don't exactly have a lot to show for that, but we do have a couple results. We were able to successfully incorporate Griffin's radiation model, and we were able to get it working for the rigid body design instead of the inflatable one. And we were able to take a look at some of the positions of food as the louver angle actually is actuating. So on those graphs on the far side of the screen here, you can see each of those curves represents one location that the food could be stored within the rigid model. And as the louver angle is iterated from 0 to 90 degrees, you can see the steady state temperature of each of them dropping as the heat radiation is leaving. And the top graph represents the outer wall food temperature, and what that is the food that is the closest to the wall that leads out to space. So that would be the coldest area. That's why you see most of the curves are below those dotted lines. The dotted lines represent our 0 to 20 degree temperature range that we're trying to stay within. So one interesting thing to note is that the only position which stayed within temperature range for both of the positions was the 0 meters from the bulkhead door to the airlock. And that's represented by the blue curve on both graphs. And then some of the future work that we plan to get done. Like we said earlier, we want to see what would happen in the case of a disturbance. That could be either the habitat module door being open or the presence of an astronaut coming in to grab food. They're generating heat, and we're going to see if that's negligible or if it's something that we really need to worry about, and maybe something that we would need to actuate the louvers to counteract. Another thing, and some other people already touched on this as well, is the size, the quantity, and the location of the louvers on the outside of the spacecraft. Would that make a difference? Is there one that's more efficient? Just some things that we're going to look at. And then
Alrighty, so me and Jordan did a bunch of background research into louvers, what has been done before, what can be done, because our whole idea was let's not reinvent the wheel, let's see what's been done before and where we can go from there. So passive louver control has been done before. It has been done on Rosetta, Psyche, and CubeSats. CubeSats are just small, like meter by meter satellites that are in low Earth orbit. Psyche and Rosetta are both deep space satellites, and Psyche is going to Psyche 16. It is not fully passive. They have passive and active louvers on there, but they do have, in some sorts, passivity. And this is done via the use of bimetallic springs that will rotate based on their thermal expansion. These right here are bimetallic springs. And here is a array of louvers. Louvers are essentially just blades that open and close on top of the heatsink to allow radiation to come in and out of the heatsink. They regulate the temperature of the modules, of electronics. They will prevent radiation from coming in from the sun when they are facing the sun. Just kind of stuff like that in order to keep the spacecraft at a adequate temperature and safe. So previous teams' work on top of all of that research done, they decided that they were going to explore the thermal expansion of aluminum rods as opposed to bimetallic springs. And that turned out to be very, very successful for them. It was very consistent. They found out that about 1 thou of thermal expansion of an aluminum rod correlates to 1 degree in temperature change, which in turn also correlates to 1 degree of rotation in the louver position. So, and that was done consistently by them. So through future work, we will be able to kind of integrate that into our own system and make a passive system based off of that, because we almost want to compare it to what has already been done by NASA and say, hey, here's another idea, or this is better than what has been done before, and this can be done consistently. We also are concerned about the louvers facing the sun. How are we going to open and close them if the louvers are facing the sun? Because that is a big issue. As when the sun is facing the logistics module, it will be providing a lot of radiation. So if these louvers are open, it'll cause too much energy to get in there and spoil the food. So that's something we kind of will have to focus on and finding a way to keep that passive.
So for designing our louvers, we started with a brainstorming process where we basically just threw any and every idea we had in our heads onto a list of paper and then started down selecting from there. Some of our favorites were putting a fan outside and having it blow the louvers open, or putting a crank through the wall and having an astronaut manually open and shut it. So we down selected those, got rid of all the bad ones. We settled on about 4 to 5 finalists. Like Brandon said, we chose the aluminum rods and the bimetallic springs are definitely the top 2 contenders. We also were discussing maybe incorporating like a gearbox or like a fluid hydraulic system to get some maybe mechanical advantage and convert like a high force low displacement into a high displacement low force application to have more louver displacement. Our most important criteria for downsizing was definitely mass and escaping Earth gravity well. That was number 1. Also reliability and complexity was another huge one, because the more complex something is, the higher points of failure that it has, and you need a lot of redundancy on something like this. Cost and feasibility were some other ones, but cost wasn't as important as the other 2. Future work, Brandon and I next semester, our goal is to look into the bimetallic springs and aluminum rods and try to see if there's a way to 100% passively actuate them. Like he said, and to cover all test cases, it probably is going to need some form of active control, but like we discussed, some active or mostly passive control, or some passive control is better than no passive control at all. So we'd rather, like you said, if we're facing away from the sun, it'd be tough to open and close the louvers if we're allowing too much energy to come in or not enough energy leaving the module. And then, yeah, the proof of concept, we're going to try to physically design something we can solve versus just try to prove that it is theoretically possible to do. So with that said, are there any questions?
Okay, thank you guys. Last questions by the committee. First, and Michael, I see that you're in the audience there. If you have questions, feel free to unmute yourself and ask as well. Bill.
Okay.
Any questions?
Let's see, I got a couple of quick questions. So starting at the end and working forward. So working with the louvers, have you identified what kind of a cycle time you have to have in terms of being able to open them or close them?
We have not specifically looked into cycle times yet. We were more just trying to like, I guess, get an idea of what could actually be possible first before getting into specifics of like how quickly we would need to open or close them based on whatever test conditions are imposed. But that is definitely something we want to look into for sure.
Okay, next question on those. Are they planned to be like either fully open, fully closed, or are they planned to be variable in their position or?
They're variable, so. Yeah, I'll move over. Okay, so they're variable, so essentially, as the angle increases, more radiation is allowed out due to the view factor that changes. The view factor is just the radiation that goes from point A to point B, or that point B sees from point A, so like point B being space, point A being the heat sink. So wanting to be able to regulate like a certain amount of temperature at a time, or a certain amount of radiation at a time to control temperature, because if there's no astronaut in there and the food is heating up, there's no need to really open them a lot. You only really need to open it a little bit, so like a couple degrees. Whereas opposed to if an astronaut does come in and the temperature heats up a lot quickly, it will open more and then close once it's done cooling the system.
Yeah, I would say it's supposed to be more of like a responsive system.
Yeah.
So as things inside start to heat up, then the louvers gradually.
So it sounds almost like you've got 2 degrees of freedom on that motion thing in terms of you want to be able to control the opening and closing when you have to release heat, but you have to also get another input from the outside and see what is the sink that you're looking at that point. And so being able to come up with that, you may wind up with like a double acting actuator that's getting that heat from the sink out there versus the heat from your payload that's behind it. Okay, so let's see. Quick tip on the coding models. If you're working in object-oriented code, make sure you're compartmentalizing. If you're working in traditional functions, compartmentalize it. You're probably finding all the previous coding, like you say, really hard to follow. But if you had separate functions that achieved this, you could go through, screen it, understand those pieces. And so as you build more for the next, keep that in mind. And then one last thing was just a quick vision on your slides. You had some plots that were in degrees C and some in degrees K. And so being able to clear either restructuring them so they're all in the same form, temperature display, or clearly identifying that quickly. I had to dig through to find in those plots which ones were which, because it drastically makes a big difference in where you are in this setting. But other than that, I think you have good things accomplished so far. Lots left to do.
Cool. I just have a kind of a 2-part question. It's a little bit related to some of the things that Bill was asking about degrees of freedom for the louvers and et cetera. But my question is exactly like part 1. What really are you trying to optimize? Like what decisions do you have available to you? What levers do you have? Is it number of louvers? Is it louver angles? Is it mechanism of louver? Is it material selection? Like what things do you really have control over in this process? And number 2 is like, what is the final deliverable that you want to give to NASA, right? Is it, you're going to make a suggestion for this number of louvers, this is what the temperature will be, this is the mechanism that we think is best, this is the material we think is best. So 2-part question. I know there's a lot there, but that's not going to be my only one. So say what you will.
Let's say. I can see where like you're kind of coming into this and you're like, what are we trying to control? What are we trying to explain to them? What are we trying to deliver them? Kind of as it's been explained to us, our goal, I mean, especially with like the simulation of it, is to make a code that is so easy to modify that if they want to try different angles or different placements or different placements or a different amount of louvers or putting the food stored differently, like that's accessible to them.
Got it.
So even though it is more of like a proof of concept, I guess, as I think of it, it's more of trying to cover as much as we can. So as they move forward in this project, they can get results.
And as you first part of your question, you were asking like, what are we in control of? What can we say? So location of louvers, size of louver arrays, how many louvers, the size of the louvers themselves, how we're actuating them, where they're placed, depending on the logistics module and the habitat module, they're two completely separate things. So if you go back to like the picture of the logistics and or the two different, or the rigid, sorry, the rigid and the inflatable, as you can tell, like you can't really put louvers here on the side of the inflatable, but you can here on the rigid model. So that is also another option. Along with, like you said, actuation of louvers. How are we doing it? Is it possible to do it passively? Just
All right, that's it for me. Any other questions? We maybe have 1 minute here. If there's anybody else that has any other question.
Yeah, first of all, I'd say it's not impossible to put louvers on a flexible structure. It's just a different challenge.
Yeah.
But because NASA looked at for, yeah, I mean, geez. This be leaves. Three leaves. My question is about what temperature you are sensing. What temperature are you sensing?
Back here for the, this was for the rigid model portion, and this was on the side that had the louver on it, so. Back here, this would be this bottom edge. It's going along this length at different intervals.
Yeah, my question is, what for the control system, for the louver control system, what temperature are you sensing? What are you using as your input for the control?
I don't know if we've gotten to the point of combining like the semester, but I see what you're saying, like what temperature is going to be sensed by Divine Metallic Springs to actuate the louvers.
I think ideally we were looking at like to cover all test cases, so have it be able to sense temperature from inside the logistics module. If it's too hot, open it up. If you're facing away from the sun, to kind of vent heat from inside, while simultaneously being able to sense heat from the sun hitting the louver, and then being able to open and control based on, I guess, both of those. Which is where we said we may not be able to completely passive to cover both of those test cases simultaneously.
Yeah. So you would like to be able to sense the temperature inside the logistics module. Ideally, which temperature would you want to sense? The food temperature. Okay. But there are challenges associated with that you are going to need to address.
Okay, let's close the session. Let's thank you guys one more time. So that'll be it for this session. We'll start up again at 10:45 with the next series of talks.